So this is a video to go over assignment 5, to give you all a little bit of an introduction. I apologize if this is a little rushed or weird in places. I recorded a full version of this video, 25 minutes long, and then found out that my computer was not recording any audio. Anyway, let's get into it. So if you go to eClass right now, you can find this assignment 5 PDF and you can follow along with me. So the purpose of this assignment is to make you familiar with procedural content generation for level design. So in other words, making procedural levels, making levels that every time you run the code gives you a different level. Here's an example output of what the levels will look like when you first load up the Unity project and you just hit play. Genetic algorithm is the specific kind of procedural content generation approach that you are going to be using for this assignment. It's a common method for creating game content that adapts to the player's behavior. So this is things like Darwin's Demons or Petals. In Darwin's Demons, as just an example, you can click on these links on your own time, but in Darwin's Demons, the enemies in the game, the little creatures in the game, adapt their behavior to you as you're playing, sort of like evolve to meet your challenge. The obvious metaphor being Darwin's theory of evolution there. And Darwin's theory of evolution is the basis for genetic algorithms. We'll talk about that more in class, and I'll talk about that a little bit more as I go through in this video. But for now, that's sort of the intuition. In this assignment, you're notably going to be implementing a genetic algorithm to produce levels to match several AI evaluators. These evaluators are basically acting as like a stand-in for human players. So you might have an evaluator that, for example, likes tight corridors or levels with more collectibles, like these little pellets, or levels with less challenge. But regardless, your goal is going to be, well, your code's goal is going to be, given one of these evaluators, producing a level that matches its specific needs. Okay, so what do you need to know? There's basically one script, and only one script, that you'll be editing for this assignment, and that's called leveloptimizer.cs. This is where you'll implement your genetic algorithm. This is where you're going to do everything. You should not make changes anywhere else but in this script. In addition, there's a script level.cs, which is basically a stand-in, our representation for different levels you might be generating. You're going to be working with it and changing its values via the code that you write in leveloptimizer.cs, but you won't be changing that script directly. Then there's evaluator.cs, which you'll be working with indirectly. Again, evaluator.cs's are going to be the sort of stand-in for human feedback, human evaluation that we will be using to guide what kinds of levels your leveloptimizer.cs should produce. So here's an example that I run through real quick. So imagine we have an evaluator named Hungry Evaluator that loves pellets. It's going to give a score of 0 anytime there's a level with no pellets, and a score of 1 anytime there's a level with as many pellets as possible. Let's say I pass in a goal value to our level optimizer plus this evaluator. If I pass in both of those things, and let's say I pass in a goal value of, say, 0.5, that indicates that a perfect level for this particular setup would have exactly half the number of possible pellets. Obviously, you're not going to be doing this by hand. You're going to be changing a random level with code with your genetic algorithm. Okay, so level optimizer, the one thing you'll be changing for this assignment, the purpose of this is basically to handle your genetic algorithm and basically all of your procedural content generation code for this assignment. So there's a number of member variables here. There's width, which is half the width of the level, height, half the height of a level, and grid size, the standard grid size for each level. And there's a few constants that you can use in your code, but you don't have to. So there's things like population size, which should be the size of each generation in your genetic algorithm. Again, we'll talk about that in just a second and more in a future video lecture. Mutation rate, which is the rate at which members of your population mutate. And crossover, which is basically the number of children, the number of crossover new things in each generation. In this case, the number of new levels we'll be producing every generation. And then we have max attempts, which is a variable that you can use to track the max number of attempts for your genetic algorithm. As with clustering, this is an approach that can potentially run forever, and so having a max attempts is a good idea. Then last but not least, there's a square obstacle, which is a set of points that can be used to define a square obstacle, which is exactly the size of a grid cell. Now, notably, you can create your own basic obstacle shapes like this using this example, but it's not necessary to get a 10 out of 10 on the assignment. Member functions. Now there's this one, which is the most important one, named getLevel. This is the main function of the assignment and where you'll need to implement your genetic algorithm. It takes in an evaluator and a goal value, and that can be used to determine the quality or fitness of a particular level. Basically, to what extent does the particular level match this particular evaluator and this particular goal value. Now it should return the best possible level relative to that evaluator and goal level. Obviously, you're going to need to alter this function. Then there's fitness, which takes in a level, an evaluator, and a goal value. It is actually going to calculate how close a particular level is to matching a particular evaluator's goal value. So in the example of above, right, if we were trying to produce a level which hungry evaluator would score at 0.5, in other words, a level with half the number of possible pellets, then we would get a 1 if we managed to do that, and we get a 0 if a level either had no pellets or all the possible pellets, and then we get some proportion of the score between those two things, the score rather. There's a mutate function, which is basically going to alter one level object a little bit. A crossover function, which will take two parent levels and make a child of these two levels. A sample function, which you won't need to alter. These other two you might find worth altering for the extra credit. A sample function, which basically samples from a population given their fitness. And a reduce function, which reduces some population back to some population size based on their fitness. And then get random level. Get random level is a way that you can produce some initial random level. Again, you can change this. It might be helpful for the extra credit, but it's not required at all for the assignment. All right, level.cs. Every level.cs value, every level.cs object created with the level class represents a specific level. This can get pretty wild, as you can see from these two examples down here. Let's talk through what you can find in here. So there's pellets, which is a list of a class called protopellet, which is basically like this fictionalized version of a pellet. And it basically specifies where a real pellet in the final level's location would be and whether or not it would be a power pellet. Then you have obstacles, which is a list of proto-obstacle, very similar, sort of a fake version of an obstacle that will represent where an actual obstacle will be in the final level. At its basic level, you can mess around with its world position, where the obstacle can be located, and shape. It's like square obstacle could go in here, and then it would say we have a square obstacle at a particular position. But you have the option to impact the obstacle color, the line width, and some other stuff. That can be helpful for extra credit, but isn't required by default. Then we have Ghost Start Pause and Pac-Man Start Pause, which is where Pac-Man and the Ghost will spawn respectively. Again, not required, but could be helpful for the extra credit. Then we have the fitness, which is used only for the reduce function in level optimizer. It's meant to basically store the fitness of this level. You do not need to interact with it at all. There's a lot of constructors for levels, which is basically how much information do we want to have pre-specified. There's a clone function that will clone you a level. This is helpful through the mutation function. And then there's a way of getting all the obstacle points. That's basically it. Then we have the evaluator.cs. Evaluator.cs has a single function called evaluate level. It will score a level from 0 to 1. There are 3 evaluator.cs scripts that you are given. Claustrophobic evaluator, which returns a 0 for a level that is full of obstacles, and a 1 for a level free of any obstacles, so it hates obstacles. Obstacle Lover Evaluator, which will return 0 for a level with no obstacles, and 1 for a level full of obstacles, except it will turn 0 if Pac-Man spawns in an obstacle. And Hungry Evaluator, which we've already talked about. Okay, so with that, let's go ahead and take a look at the Unity project. So, if we open up this Unity project, we will see this by default. We can go ahead and hit the play button. When I do that, you can see spawn in a level. After a few seconds, a blinky little agent will spawn in, try to get me. Of course, that's not possible with this level. There's way too many obstacles. Notably, we can see a fitness down in this bottom left corner. This is a 0.127 fit level. That's its fitness. You can think of a fitness as like a heuristic. It's a measure of approximation of quality. So slightly different level this time. Pac-Man could actually move around a little bit, but again, Blinky got caught. These are just random every time. This one has a fitness of 0.163. You might be thinking, what's that a fitness in respect to? Well, if we look at admin, we can look at game handler and see that this currently has the claustrophobic evaluator. So in other words, it wants the level to be as free from obstacles as possible. Now, right now, obviously, this level is chock full of obstacles, so that's not happening. We also have a goal value of 1, which means that we want a level as empty of obstacles as possible. If I switch this around to 0, for example, then pretty much immediately you're going to notice that without making any other changes, our fitness is now very, very high, 0.984. So again, we have the evaluator here, and we changed the goal value to 0, which meant that we had a much higher fitness without making any other changes. Because there were more obstacles, we basically changed things around and said, actually, we want all the obstacles possible by saying we want the inverse here, and that led the fitness to going up. But we can change this around, so we can put in, for example, the hungry evaluator. Put this back to 1, which would mean that we want a level full of pellets. We can see that our default fitness is 0.67428. So what's actually happening here? Let's go ahead and open up Level Optimizer and take a look. Let that open. Okay, so Level Optimizer has these variables that we talked about already, and there's the main get level function. What this is doing right now is it is creating a population of population size, which is 10. So we're creating 10 random levels, and then we are grabbing the best of those in terms of the fitness, and then returning that. That's obviously not gonna work because these random levels are very basic. So you're gonna have to implement the genetic algorithm to make sure that you can actually adapt to any evaluator and goal value. Let's go ahead and jump to get random level to take a look at that. So what's happening here is that we are first creating the borders of the level, as most Pac-Man levels have borders, though notably yours don't have to, depending on the extra credit you choose to go for. And then what we're doing is at every possible grid point, we're either putting a square obstacle at that position, proto-obstacle, with that value, or we're going to flip a coin and either put a power pellet in that location or a regular pellet. That's basically if we're going to pass in true, that's going to be a power pellet. If we don't pass in anything, that's going to be a regular pellet. So that's how we're getting these very basic levels. Let's jump back over here and take a look at the rest of these instructions. So we already swapped out the evaluator and goal value. Let's jump down here to the optional. Now notably, you can go ahead and you can import your own previous grid handler, A-Star Pathfinder, and the ghost code that you used for assignment 3, using the instructions from those assignments on how to do so. Notably, the only one of those that might impact the grading for this assignment is grid handler, and then, even then only if you get really creative with your generated levels. More on that in a second. Step 5 is, of course, to actually implement a genetic algorithm in the get level function of leveloptimizer.cs. I'm going to go over this approach in more detail in an upcoming lecture video, but for reference, here's the pseudocode, and I'll walk you through it right now. So to start with, what we want to do is we want to create a population, which is initialize a random initial population of size x. Now, notably, that's already happening, where our population size, x, in the pseudocode is 10, and we're creating our 10 random initial levels and adding them into our population. Okay, great. Then what we're doing is we're going to set some attempts variable equal to 0, and then while our bet fitness is under some threshold, more on that threshold in a second, and while our attempts are less than some max attempts value, we're going to increment attempts. We're going to mutate our population, which basically means that we are going to check through each member of the population and with some probability mutate it. A mutation in a genetic algorithm is some small change to that member of the population. Now, notably, that's not necessarily going to be a good change. It's just any change. So let's take a look at this code and take a look at the mutate function. Now, what that mutate is going to do is it is going to flip a coin and either turn a pellet into an obstacle or an obstacle into a pellet. You can change this mutate code, but you don't have to unless you're going for the extra credit. Then you might find it useful. Now, notably, this mutate code isn't being called at all. We could call it in this level, in this get level function. In fact, you'll need to eventually, or have equivalent code that does the same thing. But for now, it's not in there at all. Then we have crossover the population. Now, notably, this adds stuff to our population. This is basically going to produce the next quote-unquote generation, using this sort of metaphor of evolution, of the population by choosing two members of the population based on their fitness. So we're going to probabilistically sample based on their fitness so that more fit members of our population are more likely to produce children. Again, it's sort of based on the theory of evolution. Now, notably, fitness is a general measure of quality. You can think of it like a heuristic. It has many of the same sort of things going on. This is going to create a child that is a mixture of their attributes. So if we take a look in our code, again, crossover is not being called, but we can see what the default crossover behavior is. Again, you don't have to change this, though you might find it helpful for extra credit. What it does is it takes in 2 parents. It's going to instantiate initially random blank empty child. And then from that empty child, it's going to fill it in by taking the first half of the obstacles and the first half of the pellets from the first parent and the second half from the second parent. So that's it. So it's sort of taking like half and half, like the top half of the screen and the bottom half of the screen from one parent and the other from the other. Then we're going to reduce, where we take some population and reduce it back to some size x, because notably, we're going to have greater than our default x size population once we add children to our population. So we want only the best things to make it to the next generation. And the idea is that as we iterate on this, we're eventually going to get to a point where some member of our population is better than some threshold. All right, so step 6, you might want to test your code to ensure that you can generate levels that are able to achieve greater than or equal to 0.9 fitness with the default fitness function for any evaluator and goal value. Step 7, the optional extra credit, is to make changes to your level editor so that it produces levels that are as much like the original Pac-Man levels as possible, or alternatively, that represent entirely new kinds of level designs compared to the original Pac-Man levels. More on that in a sec. So grading, the thing that a lot of people care about. This homework assignment is worth 10 points as per the usual. 4 of those points just come from a correct implementation of a genetic algorithm. This is going to be tested by basically monitoring your code's calls to the evaluator and whether the fitness is rising and falling in ways that demonstrate a population that is iteratively being improved and occasionally becoming slightly worse through random mutation. As long as you don't implement like a greedy search and you don't just generate a large number of random levels and return the best one, you should be fine. And then you get 6 points for your code being able to satisfy an arbitrary evaluator and goal value. Specifically, you will gain 1 point for each evaluator your code successfully satisfies, which basically means that your code is able to get above or equal to 0.9 fitness for that evaluator, and the value, there's going to be 10 goal values for each evaluator and 6 evaluators, so 60 tests in total. You are given 3 of the evaluators that are going to be used for this test, but 3 more are withheld from you. In addition, there are 2 extra credit points. For the first extra credit point, your levels should be playable. This basically means that you should be able to, it should be possible for a Pac-Man agent to collect all of the available pellets in level. Of the 60 levels the autograder will have your approach produce, you will gain a portion of that 1.0 extra credit point for each level where it is possible to collect all the available pellets, though note, levels with no pellets will automatically pass this check. You have 2 options to receive the other extra credit point. This is where things get interesting. Either you can ensure that your output levels match the level design style of the original Pac-Man levels in terms of things like having walls of consistent lengths and color, horizontal symmetry, regular pellet placement, ghost spawn positions being unchanged, Pac-Man's spawn position being unchanged, consistent challenge to the original levels, etc. Or you can produce something entirely distinct from the original Pac-Man levels, but with a consistent style. So you can think of this as like a scale, and on both sides of the scale, it's worth 1 point. In the middle of the scale, if you just use the same random building blocks you've been given, you get 0 points. So either if your levels look more like Pac-Man, you can get up to 1 point, and for being an entirely distinct thing, you can get up to 1 point. For the left side, I'm going to be looking to ensure that your levels match the original Pac-Man in terms of the features that I listed above, for points given based on to what extent it matches. For the right side, I will use the same features as above, but I will check for the consistency of the differences to the original levels. So the features, just for a reminder, are having walls of consistent lengths and color, horizontal symmetry, regular pellet placement, ghost spawn position, Pac-Man spawn position, and consistent challenge. Those who go for the far right should have generators that produce a consistent but entirely distinct style of level. You can get really creative with this, creating what is functionally an entirely new kind of game. Let me give you a quick example of how easy it is to mess around with those. Now, notably, what I'm about to show you wouldn't give you a full 1.0, but it would put you on the way if you start going that direction. So if we open up level, and we open up Level Optimizer, we can make some pretty easy changes. So first of all of the Pac-Man obstacles are always rectangular. So what if we just delete one of these points for our square obstacle, making it a triangular obstacle? If I go ahead and hit play, we can see that immediately we have a level full of triangles, which looks pretty unique, right? Now, notably, in our level.cs, if we open up protoobstacle.cs, we can see that besides world location and shape, we can also mess around with the line color and the line width. Now, notably, you are not allowed to make changes like I'm about to do to this protoobstacle.cs class. Instead, you need to make all these changes with code. But we could, for example, go ahead and change our color so that every obstacle is, for example, bright red. Why not, right? And maybe we want to go ahead and have really thick lines. Let's take a look at what kind of levels that would produce. All right. So immediately now it looks like we're like in a cavern, right? These are entirely different from the original Pac-Man levels. This is a completely different setup, and all it took was those 3 changes. So what I'm going to be looking for is basically the extent to which your code differs from the basic starting point and how consistent it is. So how consistent stylistically is your output. Okay, let's go ahead and jump back into here and finish things off. There's a few hints just to end things. Now, obviously, you have a lot of freedom for this assignment. However, the instructor solution gets a 10 out of 10 from the autograder and only makes changes to the getLevel function of leveloptimizer.cs. Though notably, it receives no extra credit points. A good implementation can run for a long time. Warning, the instructor solution runs for 2 minutes on a 2019 MacBook Pro, which is quite some time. So take that into account. If you need help with computation power, let me know. Look for Piazza for general help and email for specific questions. You might find it helpful to implement your own scripts that inherit from evaluator.cs for testing purposes. You can look at the 3 examples as a basis. And then last but not least, you will be using a lot of random values for this assignment. Note that Unity has its own random library, which you can find the documentation for here. Last but not least, in terms of submission, you should only submit your level optimizer.cs file. If you used your own grid handler, you can submit that as well. And if you went for the extra credit and you believe it's necessary for your implementation, you may upload your A-Star Pathfinder and your code from assignment 4. Otherwise, don't upload anything else, don't modify anything else, don't upload your entire game engine. That's it. If you have any other questions, if they're general, ask them on Piazza, please. If you have a specific question, feel free to reach out to me via email. I hope that you have fun with this assignment. I think it should be a fun one.